Hey, welcome back. We are now on to a preview of one of our large scale models we'll be addressing more deeply later in the course. Um, Adaptive Control of Thought dash Rational, otherwise known as ACTR. You see here it's this sort of distributed bunch of boxes that all have arrows pointing to each other. What does that imply? That implies that information's moving around between different subsystems. So, let's get into this weirdo. First, we'll do just this to show you what kind of things this can do. This is an ACTR model written to play Tetris. This was something I did in grad school. It's the ecosystem is a Tetris environment. That environment is giving some amount of information to the ACTR model, which is, it's this thing with all the boxes. The model is written in such a way that it's able to take that information in. In this case, the information is like these potential positions, kind of hand feeding it some stuff, but it's playing the game, right? You can see here the position of the current block is represented, the position of potential destinations is represented, and the attention, the eyes of the model are this little crosshair moving around, right? Also, it gets a little confused sometimes. It starts throwing tantrums. That's kind of the key. It's able to make certain kinds of errors. Sometimes that's the modeler's fault. Sometimes that's the fault of the fact that it's trying very closely to model known things about human cognitive processes. Haha. It does everything in a very human way. So let's get to an overview of it. Come on, there we go. What is ACT-R? It is a cognitive modeling architecture developed by John Anderson in the 90s because he was interested in figuring out how children do algebra in their heads. Like, how are they doing algebra? It was from this era of, well, we can't study that. It's too internal. And he was like, we've got enough stuff going on about memory. We've got enough stuff understanding about chunks, like thanks to Miller, chunks of information that we can hold in head and yes or no. We have understanding of how errors might occur. I'm going to put all these together into an architecture. So what it is a modeling framework that allows you to draw on this sort of tool shed of interconnected cognitive modules. These modules, this modularity, everything that happens in ACT-R is done by the modules. They're models of distinct cognitive processes that trade chunks around. And remember, Miller has talked about chunks in the past. The idea, 7 plus or minus 1. What exactly is a chunk? Well, here it's defined as a blob of information that moves together. So all of the modules in ACT-R are grounded in effects and things learned and observed in especially cognitive psychology, like those kinds of experiments, experimental literature, and some neuroscience a bit. But things like, how long does it take to remember a chunk from memory? How long does it take to press a key with a finger? How long does it take to move the eyes and the attention, right? And that's another piece of this. They're grounded in the reality, so they take the same amount of time that we know humans take on some of these things. They make the same kinds of errors that humans make on some of these things. So they're otherwise altogether cognitively realistic, right? They produce behavior that, as long as it's following its particular rule set, which you as the modeler will write, it creates a believable behavioral trace. So the main thing that you're doing if you're writing one of these models is you're writing the rules, the production rules, which are essentially great big if statements that say, if the contents of my mind, my current state as the architecture running, and maybe things out in the world, everything I have access to, if things are in this particular state, I should do this. Doing something might be moving information around internally. It might be performing an action. It might be saying something out loud. It might be just creating a new sort of imaginal space, right? But altogether, it's just this big set of these rules, and then there is some pattern matching that goes on to say, okay, should any rules fire under the current conditions that I see, and which one? So the other piece that makes it very cool, this is like the reason I always liked this ecosystem, is that it operates in real time. The minimum firing rate of a production rule is 15 milliseconds. That comes from the literature as well. There is this pipeline of the minimum reaction time you can have to changing certain things internally, as observed in many, many studies, is around 15 milliseconds. So 15 thousandths of a second. That's not a literal thing. Remember, all models are wrong, but it's something that is drawn from best principles from the literature that says, hey, if we're going to have something that's able to notice the state of the world and react in time, it's got to have some kind of timeline to it. And 15 milliseconds seems like the one. What's the whole deal here? Like, what is it doing for us as this ecosystem? We'll talk more about its structure in a minute. What it does is it outputs these really robust real-time behavioral traces, right? So it will, and they are cognitively plausible, right? They adhere to the same constraints that we know of that human systems do. They produce the same errors. They behave as close to the same way as we can get at this level of analysis. And the real cool part there for the science is now you're not just comparing like, oh, did this person's entire behavioral set match, where does it fall on the line? What's the output? You're modeling the process. Ooh. You can compare directly the simulated behavioral trace from the model to a not simulated, observed human behavioral trace. The whole down to the millisecond, right? Everything it does alongside the person. And you can ask questions. You can interrogate that data. It's really an interesting approach. And even more so, not just in terms of the science of trying to like match human performance, in applied settings, this allows us to make what I have taken to calling cognitive crash dummies, right? These are tools that we give a task and an interface, and we turn the model loose and say, see how quickly it achieves things. Where does it struggle or get confused, like in the Tetris video? Where does it fail, right? Where does it make errors, and why does it make those errors? It's a very useful piece of tech to especially in like human interface and user interface design type stuff. So let's talk about the components, these modules, right? There's a bunch, a lot of them share a lot, but I have these little sort of quick versions of each. The goal module is one that you would interact with as a modeler to say like, okay, what are we actually trying to do today, right? If you don't give a model a goal, it'll just kind of sit there and it'll be like, okay, I'm just going to observe the environment or whatever. The imaginal buffer is like a sketch pad where you can keep track of information that you might want to, be changing or keeping track of things from the environment. Say pick out all the berries from this bush, visually. I don't know. I'm making things up. But so we have sort of a scratch pad. We have a goal buffer. We have declarative knowledge, which is like where all of your long-term memory comes from. And, storing facts, storing things that have happened to you, things you've observed directly from the world. They're all getting stored in a similar way inside the declarative module. The procedural module is where a lot of our work comes in as the modeler, which is us saying, this is the how-to, right? If I'm telling you to do this particular task, how you do that is determined by some procedural rules. Oh, go back. And so, it's the idea of when you're in a scenario, knowing how to approach that scenario, what to do under those circumstances, that's written into the procedural module. So these are all the kind of like internal modules, right? You have a goal, you have a scratch pad, you have some memory that you might need to access, and you have your rules for behaving. You also have input and output. So the vision module is sort of like eyes that can automatically look at the world and find things that should go into memory, right? Or go into its buffer, right? And the vision module will create chunks that the other things can ask for. Motor would be outputting key presses, right? The virtual muscles, and like how it will type tends to have like typing and mouse capabilities. And again, things like how we move our mouse are very predictable. Fitts law is part of Act R, right? The moving between things. We'll talk about that some other time. So it also has speech, so it can simulate how long it takes to produce language, like I am doing now. And it has oral, so your brain's ears, this virtual ears, where it can take information from the world, but knowing that information, like I'm doing now, takes time for you to receive. Again, it will take the information, but it will wait until it has had time to fully hear it to be able to use it. So these are all different pieces that are theoretical underpinnings of like, I think this is how a mind can arrange information in a way that's kind of equitable and useful between all the modules, right? You have this one currency, you're moving information around between them. I might see something like there's a yellow car, and then the yellow car gets encoded into the vision module, and then I can say, hey, if the vision module has a yellow car in it, I should think about all the other cars I've seen today. And it'll ask declarative memory to, hey, what other cars have I seen? That was a stupid task I made up out of nowhere, but it's kind of illustrates the idea of these different modules talk to each other. The procedural module is kind of like the main core of how the behavior is determined, but everything is kind of on equal footing. They're giving information back and forth when requested. So if you're a modeler in Act R, what are you doing? You're doing a few things. One is you're writing the production rules. You're saying, this is what I think the order of operations would be, more or less, for a person doing a task. But remember, they're kind of just all equal. So you have to set up the conditions and the actions. So any production rule could fire at any time. That's a core idea here. So the left-hand side of a rule is like the states, internal or external, that might trigger this production rule to fire. So when I say, well, if my brain is like this, and if I have this task, and if I haven't yet finished the task, then I should do this part, right? The right-hand side of the rule, if this production rule does fire, what should I do? I can make a request to long-term memory. I can update my goal. I can make a request to the motor module to press keys and like literally output key presses to the operating system. Sometimes it's great. It's kind of a fun tool if you get into it. You also need to initialize the goal buffer so that you can set up like, hey, I wrote all these rules. Now I need some initial conditions that will actually trigger one of them and get the ball rolling. And setting up the environment, right? So if you have like an actual environment you're trying to build it to interact with, you got to make sure that like Act R is its own program. So you got to be able to like, okay, give me the visual of this program I'm trying to use, right? So you might have to do some finicky stuff to make it work input and output wise. And the last thing is that a lot of modelers end up adding things to the actual entire architecture, right? Because it's extremely modular, if you're a clever Lisp programmer, which I don't advise you become, can extend the architecture by adding new modules. One cool one was like the temporal module, that has been researched and is available in the ecosystem if you want it, which allows the whole Act R structure to do things like keep track of time internally, right? So in your mind, you can sort of simulate, I need to press that key in 5 seconds. Now, right? And that's sort of a module that they bring their own research in. They cite, why am I building it this way? Again, it's all sort of bringing theory together into this computational environment where you are enhancing the capabilities of the tool. So let's do some modeling. Let's model the dumbest task in the world, counting. So the first thing the modeler would write would be this kind of thing. I'm going to set a buffer chunk in the goal module. By the way, we're going to walk through this code. Don't worry about the syntax right now. This is not a Lisp/ActR programming course. This is not like, if you do have any interaction with that, we'll cover the basics again. This is just to sort of, I'm going to guide you through it, right? So we're going to set up in the goal buffer, I'm going to set up a chunk, and that chunk will have a type, counting task, and it's going to have a current value of nothing and a max count of 2. I know, count to 2, that's the dumbest task I've ever heard, other than maybe count to 1. But it takes a long time to explain these things. So, okay, what are the production rules one would have to write to achieve this counting task? We're going to make one called count start, and we're going to ask on the left-hand side, remember, we're trying to figure out what conditions should this fire under. Well, if we're trying to start our counting task, the left-hand side is going to say, okay, if the goal buffer has a counting task in it, and its current value is nil, and its max count is some number, which is this question mark part, then, so that's the if, right? If the goal buffer has this kind of chunk in it with these values, then the output is, I'm going to make a new request to the goal buffer. I'm going to change the content of its chunk to a new setup. Mostly I'm just saying the current count. Actually, hang on. Okay, I'm back. I actually edited this a little bit. I realized that I was relying on a little overly complex thing that had a lot of redundancy in it. I don't want to waste time on. So we're doing the same thing as we did when we started. We're setting up the environment and like the goal buffer with something to get us started. So the first is very similar. Count start. If the goal buffer is a counting task, it has a nil in it, meaning we haven't yet started, then, and we don't have to track the max right now because that's not relevant to this first step. The first step is, well, then let's change that nil to a 0 and get counting. So if it's a nil, we exist in this state like, okay, we haven't yet started. But if we change it to a 0 by saying in the goal buffer right now, I want to change that value to 0. Okay. The next production rule, which would leave us in a state where we're ready to start counting. So the next production rule would rely on that change and say, okay, this is the production rule called count in head. And as long as the goal is a counting task and we have a current value, and it's not nil, and we have a max count, and the current value is less than the max count, then what am I going to do? Right? On the output end, I will, I'll first of all change the current count to be the current value plus 1. And then I'm going to ask for I'm going to make a new request to the vocal module to say the current number, right? 1 or 2 or 3 or whatever. It'll say it, in quotes. And then finally, the last thing we need is a stop condition. So you can probably guess if the goal module is a counting task, that helps to make sure that these production rules fire only if we are doing counting task, right? The current count is cur and the max count is max. If the current count is above or equal to max, then we'll say the vocal module should say done, and the goal, we're going to set the current count back to nil because we are no longer in task, right? So these are 3 production rules for the dumbest task in the world, but this is still the process, right? And remember, one of these can fire every 15 milliseconds. So think about how, okay, count to 2 and then say done. 1, 2, done, right? I'm saying that with my human words. My brain probably did it even faster. So let's walk through the execution stack, the execution trace for this situation. So first, timestamp 0. This is like before the models even started and had a chance to do anything. What's in the goal buffer? Well, we set it to be 0 and 2. Pink in this case is representing the new information, right? There's not going to be any procedural rules fired this first step because nothing interesting's happening. We only started. And then the vocal buffers, nothing's happening on the talkie end, right? Timestamp, the next timestamp, 15 milliseconds later, the goal buffer is still going to have what it had in it, right? Nothing has happened at this first step. But now is when we have the question, should a procedural rule fire? Of our 3 conditionals, which one should fire? Well, right now, we have nothing in current count, so neither of these can fire. But we do have nothing in current count. This one is allowed to fire. So count start fires. And that means, not right now, but the next step, this will be applied. The change will be applied. Let's watch it happen. At 30 milliseconds, we change the value to 0 in the current count value. And no procedural rules are going to fire right now because nothing new is happened, and count start can't fire immediately again. And we haven't said anything because that's not what happens. All we did here was change a number. Now we go to 45 milliseconds and we've got 0 and 2 still, because it's inherited from the last time. But again, we're going to enter, is there a production rule that should fire? Under this circumstance, which production rule fires? So we're at this situation of 0 and 2. So it's not nil. The current count isn't nil. The current count is less than the max, and it's not greater than or equal to the max. So this one fires. Count in head. Okay, so now we do this. Count in head is going to change the content of the current value. It's going to not fire immediately. And we're also going to say 1. We're going to ask the vocal buffer, hey, take this 1 and output it as a simulated, speech. We continue on. This happens again because we're still not there to our destination yet. We say 2. We count to 2. And then finally, we get to the case of, hey, 2 and 2. That means count done, because that means we have the same value or greater than, potentially. So what I'm going to do is change the value back to 0 and say I'm done counting. Pardon me. Pause to cough even more. Ugh, getting phlegmy. So this is a behavioral trace of one of the simplest tasks one could even imagine. But notice it's playing out in 12 hundredths of a second, right? It's playing out in 120 milliseconds. Now, it takes you a little longer than that to actually say things out loud. The vocal buffer would just have the cue. It would be like, okay, I'll say 1 and 2 and done as soon as I'm able to, because I have to say 1 before I can say 2, right? So that's the idea. But then take us back to setting up. Imagine now you have many, many, many cases here. You have many production rules that can be triggered by different scenarios that are happening in the world and inside the system itself. And you end up with a system that can play Tetris. I'll leave the music. And remember, every 15 milliseconds, let me bring it down. It's too much. Let me blow out your drums. My bad. So every millisecond, I'm gonna mute it again because we got that background. So every 15 milliseconds, we'll pause. It stops and it says, okay, what's going on in the visual world? In the visual world, there's at least the position of the current block and then some other options for where to place that block, right? Those options might require rotating the block, which would then be its own subroutine. Like, okay, if I'm going to move this block over to the right and then place it, then I need to engage in a new subroutine of every time my motor's ready, every time my simulated thumb is ready, hit the right button, hit the right button, hit the right button. Let's watch it play out a little bit. It goes right, right, right. And then it hits drop. It even knows how to drop. So it's able to continuously check the state, make a decision, check the state, make a decision. And again, it's doing it all in cognitively plausible ways. It's like saying, hey, I know it takes 150 milliseconds for something to reach my fingertips to be able to be pressed. That's why it doesn't just instantly slam it to the wall in this superhuman way. It's following the constraints of humans. It takes it time to shift its attention around. You see the attention is always moving about. You see that it can get confused. Well, no, I guess it does okay here. I wouldn't make that decision, of course. That's a bad Tetris move, but it's able to make that call. In the future, one would add better like strategies to this system. And then finally, it gets a little confused and it starts looping because when I originally did this, I didn't set up the production rules very well. So it throws a little tantrum and just rotates the block eternally until it lands. So I hope you can see where being able to emit human-like behavior in a complex real-time task is actually super useful. So come on, move on. There we go. ActR is used in education. This was the original use case for it. It can help you build, cognitive agents for if you're trying to set up training, right? So if you're trying to set up a system where you want things to behave in humanish ways, you can use it in evaluating your interfaces. You can use it in psych, of course, because we have it makes all these scientific predictions that we want to evaluate. But it's useful in other places too. There's even some neuroscience stuff been added in later years of the development where they're trying to actually tie the activation of like the goal buffer and the imaginal buffer and the vocal buffer to brain region activity. Long process with mixed results, but it's an ongoing evolution. It's great. So yeah, that takes us to the end here. So we're going to revisit ActR later in the course. For now, the key things to know about this modeling architecture are its human-constrained real-time behavior traces. Very cool stuff. If a model can be described here in this system, it's going to be cognitively plausible. Again, is it going to be true? No. That's expecting too much. But is it a good guess? Is it a useful guess, right? And even better that it's plausible. If it takes a human X amount of time to press a button to remember a fact, it takes ActR that long as well, right? It doesn't get to cheat. It must play by the human rules. I love the application of them as cognitive crash dummies. I mean, I use these to evaluate ballot cognitive fallacies and errors in during my postdoc. And this is like, you create simulated users, right? You can assume a user kind of knows what they're trying to do. Thus, you program the production rules to do the task, but then showing it different versions of the same interface, you can see, oh, this one makes a ton of errors because this thing is hidden in a menu that it lost track of or something. Now, again, you have to be kind of a skilled modeler to know what can and can't be set up here, but I think this is really cool, especially if you're in like HCI realm where you can set up ActR or a version of it to just literally navigate your website and see what it does, see if it fails, right? And last bit is, this is just like a general modeling thought. This is a more symbolic system than a sub-symbolic system. It doesn't rely on like a lot of low-level computations of simulated pieces, like little like artificial neurons or things like that, like in maybe Spawn or AI. It's more symbolic. It's like, okay, the rules are you can move this information like this. If you move it this way, this will happen, right? It's all sort of symbolic level. And that's what makes it fast. That's what makes it decent, but it's a level removed. It's slightly more abstracted. It's closer to math, math modeling than it is to, well, I mean, it's situated between like a super low level, like neural simulation and like a simple output, statistical model. It's somewhere in between, right? It has lots of rules for how information is allowed to move around, but at the same time, it's producing real-time data, real-time behavioral data. So I think it's pretty cool. So yeah, it exists at the level of cognitive tasks, not way up into like psych phenomena over your lifetime, and not down into like neurobiological simulation. It's sort of at the level of how do I, navigate a web page or interact with this cockpit or something. So yeah, that's Act R. Nice little preview. More soon. Take care.